Hey guys, good morning. Welcome to the last day of S4. I just want to start off the talk by letting you guys all know that all the information that I'm going to be presenting here today is TLP Chris Krebs' pants. So that's going to be red or orange, kind of depending on whatever lighting you see here. So handle that information accordingly. I'm totally kidding. Everything here is shareable. It's fine. So you guys were all told that you would be seeing a presentation today on DER attack vectors. Kidding. I'm watching to see who gets up right now to figure out who my real friends are. I figured it's day 3. We need to laugh a little bit, right? So if you turn in your S4 hymnal to my speaker bio, you can see kind of my formal background with the lab and FireEye, but I figured I would add a little bit of additional information since this is my first S4 talk and not all of you know me. So I like to joke around that I was raised by a clan of feral engineers, specifically in manufacturing and oil and gas. And this is relevant because when I was about 8 to 10 years old, my dad used to take me on the plant floor and show me around and show me how everything worked, which was super interesting and gave me a lot of really great insight that I now use in my professional career. It's also hilarious to me when people want to use industrial safety as a model for industrial cybersecurity, because in industrial safety and OSHA standards, things still end up on the plant floor that aren't really authorized to be there. So anyways, back to the story. So why are we here? So when I first started at Oak Ridge National Lab, my mentor, Mark Buckner, who's now retired, gave me a really good piece of information that I've carried with me, and that is that everything is a remix. None of us are out here reinventing the wheel on our own. So we're looking at the problems that we're facing and looking at the work that our colleagues are doing and the research that's been done, and we're thinking critically about it and adding our own spin to it. So 2 years ago, there was a set of papers that came out by a set of researchers in Princeton that were looking at, if I had a botnet of high wattage IoT devices, could I mess with the frequency in the grid to cause disruption? Basically, they did some modeling, and it's really interesting research, but this is basically looking at what we now call demand-side attacks. And for any of you who aren't familiar with that term, essentially all that means is that instead of trying to get into your substation, your relays, your generators, I'm going to try to get into the devices on the consumer side that are consuming that power from the grid and affect them in a way that may mess with things a little bit. So just for any of you that weren't familiar with that term beforehand, that's all I mean when I say that. Also, I'd like to disclaimer right now that if you came here looking for the next Sky is Falling sequel to The Grid, you're going to be super disappointed. This isn't anything that is going to be like super fuddy or have anything like that. So please don't quote me making me sound like an alarmist. I will be really, really heartbroken if you do that. So the research area here. So I got to thinking based on their research, because most of their focus was that, you theoretically could do this, but in a traditional power grid situation, the system inertia is going to make up for it. So you're going to have some kind of rotating kinetic mass that's going to give you the inertia that's going to be able to act as a buffer for any kind of frequency disturbance that you would really be able to have by getting your hands on air conditioners. So I got to thinking, okay, that's great, but the power grid is changing. Like the nature of our power systems are being affected by all the integration of DERs such as solar that don't have system inertia. So as a threat actor, can I target LowInertia systems with these? And what does that look like as an attack vector? What would I need? What do I have at my disposal? What's built into these things that could stop me and make me less effective? So that is how we arrived at this particular area. I don't know if any of you were in Tom's talk earlier this week on inverters. This kind of ties into that a little bit. So why demand side versus utility? Hasn't this been disproven already? The answer to that is only kind of. So when the researchers initially published the IoT botnet stuff, a lot of the people in this room kind of raised their hands and said, hey guys, like that's great, but you at best may be able to cause temporary, really localized disturbances on the grid with frequency. So I completely agree with that. However, I do think that this is an attack vector that we kind of need to keep our eyes on because power systems are incredibly complex. We've seen that over and over and over again with Ukraine. And there are still some factors that go into demand-side attacks that make them pretty attractive from my perspective. One of our colleagues likes to joke and say that you can't hack what you can't touch. And I would like to hijack that and say that you also can't patch what you can't touch. So if I'm able to get into something that is totally outside of the utility's jurisdiction and mess with it, David Lawrence is shaking his head yes right now because we've had this conversation before. It makes it really difficult for Duke. Like, I used to do threat intelligence for FireEye, and we would do recommendations at the end of every threat intelligence report that looked like, I mean, we all know the list, patch your stuff, segregate your networks, the list that we all know. But what does that look like if the actor is on footholds that you have zero jurisdiction over, which is kind of the fun thing about demand-side attacks. And also, there's a lot of talk about the grid being insecure because individual components are insecure. You know, your SEL relay doesn't have great security built into it. The passwords are all out there on script or whatever. But I think sometimes we miss the forest for the trees a little bit in that the grid's true single point of failure is our ability to be able to ballpark the load. That's why this whole system works. So if we can go after that as attackers, that's really going to cause some heartburn for people like Dave. And that this isn't the only way to do that, but this is one way that you can. So also, in that same vein, everyone likes to talk about Ukraine when we talk about grid security. And the folks at Dracos, I think, did a really awesome job with their Electrum paper this summer, kind of calling out that, we can get into certain relays, but because of the redundancies built into a substation, that might not have the kind of effect that you were hoping for, even if you're able to get into different singular devices. So it requires a pretty deep technical understanding to be able to affect this stuff. But what requires still a decent amount of technical chops, but much less protection engineering, is being able to get into consumer devices on the other side of all of this. And also, I wanted to point out, because I thought Dale's panel on day one brought up some pretty good points as far as the legality of all this, and it's what I did my thesis on, is that it's pretty easy to say, Russia got into a substation and it did this, and this is pretty clearly attacking critical infrastructure with cyber network operations. But from a legality standpoint, this gets a little fuzzy if we're doing this on home devices. If I'm not actually touching your critical infrastructure, I'm just using something kind of unrelated to mess with it. So with the Princeton researchers, they were specifically calling out air conditioners, and this has kind of become like the colloquial for those papers is the air conditioner attacks. And so just for anyone that doesn't have this background, this is kind of generally the wattage that we're looking at when we talk about smart home devices that are high wattage-ish. They range from about 1,000 to 4,000. For your air conditioners, your heaters, so you would need a lot of them. When the researchers from Princeton were doing their research, they established that you would essentially need 15 to 20% of all air conditioners synchronously going on and off in any given area, which finding 20% of air conditioners connected in any area and being able to get into all of them is still pretty hard. But now we don't have to only focus on one particular device. This is really funny that we have cyber pranksters now that are getting into people's homes and getting privileges on the entire house and being able to affect multiple devices at once. And they're able to make it essentially make any family feel like they're at my house on any given day in December. It's funny, it's not. But essentially, the wattage of any given entire home is going to be more than the individual components, so that adds a little leverage to the bar for me as a bad guy. And also we have gems like this. I would hate to say that these are uncommon, but unfortunately we're still adding super unnecessary connectivity to industrial equipment. We're still dual-homing workstations, and by we, I mean engineers, and not all of them, but. And you still have, your third shift operator whose phone's almost dead, and it has a really great USB port that he can charge his phone on? his HMI. So there's that air gap for you. And this is significant because this is a lot more bang for your buck wattage-wise. 1 horsepower is about 750 watts. So a CNC machine that they use to make everything from washing machine parts to grenade shells can go from 40 to 70 horsepower and runs continuously. So if I can get into one of these, that's the equivalent of getting up to maybe like 70 air conditioners in one machine. And I'm assuming most people in this room are pretty familiar with how terrible the security is on these things. They're not great. I mean, they're worse than most modern consumer IoT. So I'm sure that all of you are now conditioned like Pavlov's dog to assume that since I mentioned IoT, I'm going to show you Shodan. I'm not going to show you Shodan. I'm really sorry. We don't have time for that today. For any of you who aren't familiar with Shodan, no shame in that. If you want to talk about it afterwards, you can come find me. We just really don't have the time space for it today. I am going to show you this, though, because this is super significant to trying to model demand-side attacks. Because for me to model a demand-side attack, essentially what I have to do is say, okay, how many connected devices are in a given region? How much system inertia is in a given region? What does the load look like? What are kind of my fragile days on the grid as far as power consumption goes? And there's a really big problem with doing that modeling, and that is that some of these are honeypots. So if I think there's 400 and there's only maybe 200, that makes modeling all of this really hard. And it's also kind of a pushback that we get about, there's not really as much of this on the internet as you think there is, because so much of it is honeypots. So I wanted to give up an example that isn't, that I can talk about. This was a device that I found that was internet-facing at a major engineering college. And I called them up and I said, hey guys, because I found it and I saw it belonged to them and I kind of wanted to get permission to play with it. So I said, hey guys, is this a honeypot? Like, can I play with this? And they said, what? What is a honeypot? So long story short, this wasn't a honeypot. This was one of their engineering students had made this internet-facing. So you can find this stuff on the Shodans. And also, my employer asked me to make sure that I called out for anyone that works for Schneider that's in the audience that's getting a little bit of heartburn right now, maybe. This is not like a vendor issue. This isn't, Schneider has a O-Day that's making this internet-facing. This is a misconfiguration problem on the engineering part, or in this case, engineering students. So what? So what does any of this have to really do with low inertia systems, with distributed energy resources? So in the past, we had enough system inertia to make up for this. So if you wanted to make that frequency flux 1% up or down, you would have to cause a pretty big demand spike or drop. And as our system inertia is decreasing because we're having more and more solar, more kind of old school wind that isn't providing a lot of inertia back to the grid, all of a sudden I don't really have to get as much of this, as much of a drop to cause a difference. In a light inertia system, over time, I can cause that way, way, way easier now. So feasibility. So I promised you no FUDs. We can talk about this. So a lot of this depends on where you're trying to hit, how much is actually available to you, what the days look like, what the weather looks like, because that affects all of our clean energy. So when we're trying to model all of this, these are kind of the big factors that we have to look at. You have to figure out how big of a botnet do I need if I'm targeting a specific geographic region, if I have any hope in the world of causing that kind of significant frequency disturbance that's actually going to make a difference. How much DER penetration is there, not only in general, but also at any given time during the day, because that changes. And also looking at your periods of highest risk. So when is that DER penetration going to be the highest so that the system isn't going to make up for it? As far as things that can mitigate this, we do have, if you go on IEEE and search virtual inertia, I mean, you'll find 100 papers from the past 2 years. So there are people working on getting virtualized systems that are able to mimic kinetic inertia and make up for some of this, but we're not quite there yet. And some of the storage capabilities that we have that are supposed to be making up for it, the technology is still imperfect, and it still breaks, and things still shut down. And as far as the actual ability to cause disruption on the system, I also want to point out that you don't have to cause a frequency drop. You don't really have to make anything open or trip or, hurt itself like they were trying to do in Ukraine. If I can cause load shedding, that's a blackout to someone. Your power is still going off. If I can make the utilities go, crap, I have to shed load, I'm causing grid disturbance. I'm making a bad day for Dave. I'm picking on you. I'm really sorry. I'm not sorry. We'll talk about it at the next IAB meeting. So what is the Oak Ridge National Lab doing about it? So this is going to be my shameless Oak Ridge plug, both because I love where I work and because in order to have a charge code to come here, I have to talk about ongoing projects. It's funny because it's true. So we have a couple of different research projects right now that both tie into this research directly and indirectly. FNet and Eagle Eye that we use to model the frequency on the grid, and a bunch of different other aspects that we can look at and how that would affect the frequency on the grid, such as solar penetration and earthquakes, all kinds of crazy stuff. And then we also have, my team specifically is teamed with a company called Brixen that has manufactured these little, they're called arena devices that go into residential homes, businesses. We have a bunch of them deployed down in Puerto Rico to look at some of the frequency anomalies happening there after the hurricane. That's really interesting research. And looking at future research at leveraging all of this in order to kind of figure out and model in a more true way, if someone was going to try to conduct this kind of attack, what would it look like? So what we've been looking at doing is basically doing I can't talk today, a combination of doing some ArcGIS modeling with a bunch of the data, and I have to have Shodan in here somewhere, and some of the different NREL data in order to kind of try to figure out where are the most at-risk areas in the country for this. Where has the highest penetrations of DER with the most connected devices and high-risk times during the day, and who may not have enough of the mitigation technology in place to make up for this, should a bad day come. And if any of you are interested, I'm not going to show the video right now, but there is open source FNet and Eagle Eye stuff that you can look at that you can basically go on and watch the entire frequency reaction to the Florida blackout that happened. That's really, really interesting. And we are using some of this to try to model some different frequency disturbance situations. And then these are our arena devices. We've been looking at using these for monitoring wide area networks, specifically looking at DERs, trying to figure out kind of what that looks like from a large scale standpoint for frequency stability and monitoring. We've been looking at actually putting them in solar plants to do some modeling on the frequencies with the solar inverters, doing precision analysis for high PV areas, and so on and so forth. This is just some general specs on these that I'll go through for any of you who want to snap pictures of it. You can ask us questions afterwards about it. And then this is basically what that interface looks like. So on our back end, this is the frequency that we see at the National Lab when we're looking at the output from these devices. We've done some really interesting stuff in the past week looking at some of the disturbances that are being caused by natural events to frequency that we're still kind of trying to figure out exactly why that's happening. And that is the end of my presentation, and I would love to open up the floor to any questions you guys have. This is fair. I've picked on you enough. You deserve to ask a question.
So why was the dryer not on the list? I have 3 questions.
I actually don't know why the dryer wasn't on the list. It's a high wattage-ish device, but yeah.
Do you know of anybody that's put together, for example, a Nest or Thermostat hack where they actually aggregated a whole bunch of them and drove load up or down to do your load curtailment thing? Has that happened anywhere?
Not that I'm aware of. When I was at FireEye doing threat intelligence, they did have some indicators that there were, not in North America, there was some stuff in South America, that there were some IIoT botnets going on, okay. But whether those were being aggregated to cause this kind of stuff, we didn't really see any evidence to suggest
I
that.
guess, do we trust Google, because they could take out a big chunk of,
Yeah.
of load or drive load up like crazy. And then the last question would be, since you've been involved in this space so much, and not to be super judgmental, but I am an ESTJ like crazy, so how did Sunspec happen?
How does what?
And Sunspec happen and the lack of security. But how did this happen?
How did what? Sorry, I can still can't hear you.
Sunspec
Oh.
Modbus for the control of the inverters.
No, it's the inverter stuff is really interesting from my perspective, at least, because we all love to hate on Huawei. You know who makes all your inverters? It's Huawei. So yeah, like the security on those things isn't great at all, and a lot of them are connected. And that's an area that we're actually doing some GMOC proposals for right now.
So related to the inverter issues, connected to those, we're starting to see DER management systems, so DERMs coming in that can accept weather forecast data from external sources to help predict the PV so that they can reduce dispatching on generation. Do you see the value of the ARENA devices and the modeling that you're doing to be able to feed into something like a DERMS to help avoid the load shed issues, or do you see those as separate issues altogether?
So we haven't looked at them specifically for that application. That would be an interesting use case for them. Right now, we've mainly just been using them for like the data aggregation on our end for some different things that we're doing.
Okay, great, thanks.
Yep.
I'm curious if you've looked at all in terms of the ability to impact frequency of a cascading attack where in a low inertia system you could actually push frequency temporarily below 59.3 and have your legacy 1547 inverters, your 1547 2003 inverters trip offline, then creating additional lack of generation.
Sure. Yeah, that is something that we've been looking at. Some of the students at Current are actually have shown a little bit of that with some of their low inertia system research. You're still generally going to catch it 2 or 3 down the line. I hate to suggest that you wouldn't. I foresee, kind of the Con Ed situation where there's other failures that are playing into my hands as a bad guy that make that possible. But I still think it would get caught, 2 or 3 down the line before you would really actually see that.
Thank you.
So one of the questions I had got asked, great answer about the arenas as a DERMS sensor. That actually sounds interesting. So I asked this question to one of the engineers. You'd called it load shed, and he corrected me and said, no, it's interruptible. It's not load shedding. There are customers that are interruptible. What would you think about
Dave's
that
laughing.
answer? Yeah, I know. I almost mentioned this to Dave too. What would you think about that as a response tactic of a distribution provider to say, well, we're just going to go out and get more contracts for the CNC machines and the other, one of the bigger ones we have, they use electricity to melt metal. And when that turns on, it's a pretty big load, but they get really low rates so that when needed, we can turn off their power at a moment's notice. Would you consider that a problem, or would going out and getting those contracts and building that be a legitimate response to this threat?
So this is something that we've talked about a little bit. You're still turning off their power. Yeah. Because we had talked about, can you put sensors on buildings, like individual industrial park buildings that would be of higher risk, that, if someone did get into them and start causing this kind of madness, we would be able to interrupt them, as you so nicely put.
Interruptible, yeah.
And if I'm a mom and pop manufacturing shop, you turning off my power is pretty problematic.
It is.
And I'm not going to be real happy about it. So I think that's definitely something that needs to be taken into consideration, because the kinds of places that you are talking about interrupting are really high financial impact places to turn off. Yeah. And that affects a lot of people if we turn them off. So I think as an industry, we really have to be sensitive to kind of all aspects involved if we're going to look at those kind of solutions.
Cool. Thanks.
Hi, nice talk. Are you more worried about voltage instabilities or frequency instabilities? So if you tell me there's a frequency instability problem, there are things like reserve margins where generators can spin online fairly quickly, and that helps with the frequency problem. But voltage, I don't know how to think about that one. Which one concerns you more?
So I'm personally a little bit just more concerned about the frequency instability because that's really what you're lacking in the low inertia system. So if you have low inertia, you don't really have the kinetic mass that's going to help you buffer to stabilize frequency. And between that and the load shedding, I think that's really the two big parts that we're looking at here, because I think those are going to be what goes first.
Thanks.
Any other questions?
Any more questions for Maggie?
All right, awesome. Thank you guys so much.
All right.